Good morning, everyone. So, last topic of inorganic chemistry, that is Unit 1, and which one is boranes and carboranes. These two are commonly known as clusters. And let's see the definition of clusters. What is a cluster? Cluster is an ensemble of bond atoms or molecule that is intermediate in size between a molecule and bulk solid. So cluster is a nothing but is an ensemble means assembled or a combined of combination of atoms or molecules that is intermediate in size between a molecule and bulk solid. So here see before going to this, what do you know about molecule? So molecule is a smallest individually existing part of a compound or we can say element, and that molecule may consist of more than one similar or dissimilar atom. So the size of this cluster lies between the molecule and bulk solid. So in between. Okay. So how we can prepare a cluster? Just a cluster is an ensemble of bonded atoms or molecules. Okay. So we can expect the cluster it may contain more than one molecule. Okay. And next cluster exists of diverse stoichiometric and nuclearities. So here these clusters may exist diverse, it means different stoichiometries. So stoichiometry means generally what we expect 1 is to 2, 2 is to 1, 3 is to 1. For example, if you take NaCl, in that sodium is 1 proportion and chloride is 1 proportion. If you take MgCl2, so in that magnesium 1 and chlorines are 2. So then we can say 1 is to 2 proportion. And the nuclearities means same atoms, the central atoms are we can say nucleates. Sodium in NaCl, sodium is one nucleus and chlorine is another nucleus. For example, carbon and boron atoms form fullerene and boron clusters. So fullerene is nothing but a allotropic form of carbon, and likewise boranes generally formed by the combination of boron and hydrogens respectively. The transition metals and main group elements form especially robust clusters. Robust means strongest cluster. The cluster can also be consist solely of certain kind of molecules such as water cluster. Okay, so this is about the cluster. And next, so this word is coined by F.A. Cotton in earliest 1960 to refer a compound containing a metal-metal bonds. In another definition, a cluster compound contains a group of two or more metal atoms which are direct and substitutional metal bonding is present. So actually it is not in our syllabus, but actually we have boranes. So next, boranes are also one part of clusters, and these boranes generally consist of boron and hydrogen by the combination of boron nucleus and hydrogen nucleus, and these are on the basis of their structure and formula, and these are three types: clozo, nido, and arachino. Okay. So see next, how we can describe the properties, or how we can predict its shape, and how many uh, shape and how many nucleus present at vertices, or we can say vertices, or we can say apex. So that can be found with the help of this Wade rule. Okay, let's see what is Wade rule. So Wade rule, generally methodology to follow when applying the Wade rule is follows. Okay, so how we can apply this Wade rule? So to apply this Wade rule, we need to follow some certain rules. Okay, so first one is determine the total number of valence electrons from the chemical formula. So the chemical formula means nothing but a molecular formula. From that molecular formula, the first and foremost thing is to do is to find the number of valence electrons. For so valence, what are valence electrons? Again, just recall your previous knowledge. So see, in a molecule, in an atom, we may have two types of electrons: valence electrons and core electrons. What are core electrons? The electrons which are present in inner shells. And what are valence electrons? The electrons which are present in outermost shell. Okay, so generally we consider unpaired valence electrons, that means single electrons. Okay, so here see in the boron, if you know the atomic number, if you recall the atomic number, the boron atomic number is 5, and if you read the electronic configuration how we can write 1s2, 2s2, 2p1. So 1s2, these two electrons are inner electrons and the outermost shell is 2. So in that second shell, we may have two suborbits, that is s suborbit and p suborbit. So those may be designated as 2s and 2p. So here, if you write the electronic configuration of boron, so how we can write 1s2, those are inner electrons, and outer shell is 2, 2s2, 2 electrons, and 2p1. So total how many electrons do we have in outermost shell or farmost shell? 3. So these 3 electrons are considered as a valence electrons for whom? Boron. In case of hydrogen, so atomic number of hydrogen is 1, and if you write the electronic configuration of what will be the 1s1. So that means how many valence electrons? 1. So first we need to find the valence electrons of each and every constituent of a compound from its molecular form. And then what we need to do, we need to subtract the 2 into number of BH bonds or BH units. So 2 means that is the each here the boron and hydrogen we can expect only covalent bond. So each and every covalent bond may contain 2 electrons. So we need to subtract the whatever total number of valence electrons minus 2 into number of BH bonds by 2. So that means that the whatever number we obtain from this, that will be divided by 2. So what we get, we can get SEP. What is SEP? Skeleton electron pairs. So this skeleton electron pair is very, very important. Okay. So what is skeleton electron pair? So what we get from that? So what information provide this SEP? So see, so here just now we studied that. What we studied? We studied that we have 3 types of borans. One is clozo, nido, and arachno. Okay, so with the help of this SEP, we can get the idea about the structure of boron. So SEP. So how we can get the SEP? SEP is equal total number of valence electrons minus 2 into number of BH bond by 2. That will give what? SEP. SEP means skeletal electron pairs. So see, so here in a cluster we have number of, we have n vertices. Vertice means telugulo shikharalu antam. Vertice. So at that vertice, this boron atom will be resided. So at vertice, or you can say corners, or you can say apex. Apex means shikharalu points, or you can say in simple terminology we can say corners. So that means each and every corner of a cluster will be occupied by whom? Boron atoms. Okay, so the n is nothing but vertices. If all vertices are occupied by boron atoms, then we can say n is equal vertices that equals to the number of boron atoms. At that time, in that case, n plus 1 if equals to SEP. So n plus 1 equals to SEP. So then the structure of that compound or the boron is what? Closure structure. If in case of another cluster where the n minus all, so how many vertices do we have n vertices, but out of all vertices except one vertices. So generally these vertices corners are occupied by whom? Boron atoms. If the number of vertices equals to number of boron atoms, at that time n plus 1 equals to the SEP. So at that time what will be the structure of our boron closure? If the vertices, how many? N. So these out of n, if except one, all vertices are occupied by boron atoms. So that means at that time we can say n minus 1 vertices. So n minus vertices will be occupied by whom? N minus 1 number of boron atoms. At that time n plus 1 will equals to SEP. So in that case, the structure of our boron is nido. If n minus 2 vertices, the number of boron atoms, if equals to n minus 1, then the n plus 1 equals to always equals to SEP. So it is common. Okay, n plus 1 that is common, n plus 1 that equals to the SEP. So a part of this, if nr equals to number of boron atoms, then the shape of that compound is closure. If n minus 1, the number of boron atoms resided on corners or occupied carbon is n minus 1, then that structure is nido. If the boron atoms occupied resided on that corners or vertices is n minus 2, then the structure is arachno. Okay. Let's see example. So how we can do all those things, calculation part. Okay, so total number of 1 minute. So if I reduce this size, oh sorry. Okay, so example one, what is the structure of B5H1, that is boron. So in that first step is what to do, what we need to do, we need to calculate the total number of valence electrons. So how we can calculate the total number of valence electrons? So 5 into B, that is number of borons, plus 11 into hydrogens. So what is the valence? Each boron can contribute how many valence electrons? 3 valence electrons. So that's why it will be taken as 5 into 3 plus, and each hydrogen atom can contribute how many valence electrons? 1. So that means 5 into 3 plus 11 into 1, whole total how much? 26. Now this 26 to be subtracted from the number of BH bonds. So from this formula we can simply assume that how many boron and hydrogen bonds can be expected? 5. So 5 to the 10. So that means this 10 number electrons, 10 number should be subtracted from 26. Then we can get 16, and then that 16 to be divided by 2. So at that time we get SEP. What is that? SEP. SEP. So now see how we can get the n value. So if n plus 1, so always SEP equals to how much? 8. So that means SEP is how much? N plus 1. So that means n should be, easily we can guess n how much? 7. So if n minus 2, that means 7 minus 2 is 5. So if this 5 is equals to number of boron atoms, then the structure of that boron is, what is that? Arachno. What is that? Arachno. Arachno. And based upon the we can so if it is arachno, then its structure may be pentagonal bipyramidal with 2 apexes missing. So that means in this molecule, in this pentagonal bipyramidal, we can expect how many vertices? 7 vertices. Out of 7 vertices, 2 vertices are missing with whom? Boron atom. Missing with boron atom. So that statement he implied as, or he said like that, how with 2 apexes are missing. Apexes means are nothing but vertices. Okay, so this is the way to calculate or to determine the structure of given boron. And next one is okay, so next one is, so another, let's see another example. Okay, so another example, that is Closov. General formula of the Closov is Bn Hn minus 2. So here n is what? Number of boron atoms, you can say. So it is an hexahydroboron. Hexaborate minus 2. The charge is how much? Minus 2. So in this case, so how we can calculate SEP? Tell me, what is SEP? SEP is total number of valence electrons minus 2 into number of BH bonds by 2. So how we can do? So how many boron do we have? 6, and each boron can contribute how many? Tell me. Sorry. Oh, okay. So how many SEP is equal? Sorry. SEP is equal. How we can calculate? SEP is equal total number of sorry, boron atoms how much? 6 into how much each boron can contribute how many valence electrons? 3 plus how many hydrogens do we have? How many? Yes, how many? 6. So each hydrogen can contribute how many valence electrons? 1, 1. Okay, minus. So now I will place a whole this thing in parenthesis. Okay, next minus. So 2 into 2 into number of BH bonds. How many BH bonds we can expect? We can expect 6. So that means 6 divided by how much? 2 divided by 2. So that will give ourselves. So by that formula, how we can get how much? So is equal 18 plus 6 how much? 24. 24 minus 12. 12. 12 by 2 how much? 6. So SEP is how much? 6. SEP how much? 6. Okay. So now if SEP is 6, further it is equals to how much? It is equal to how much? N plus 1. So where n is equal to how much? 5. 5. Okay, here we have some other examples. Okay. Okay, the example is 6 into okay, minus 2. So minus 2 indicates what? Again, gaining of 2 electrons. Sorry, minus 2 indicates what? Gaining of 2 electrons. So that means how much? 18 plus 2, 20, 20 minus 6, 26, 26 minus 6, 20, how much? Sorry, 26 minus 12, uh, 14, 14 by 2, how much? 7, sorry. So it will be the 7. Sorry, extremely sorry. Okay, 7. So where at that time, n how much? N could be 6. N could be 6. Okay. So according this formula, according to the weight formula, so what is it? So if no, what is that? Okay, here. So if SEP is n minus 1 vertices and n plus 1 is the SEP, then the structure is Nido. So where n is equal this one. So what is the structure of this compound? So what is the structure of this compound? Closure. Why? Why? Because if n is equals to number of vertices, all vertices are occupied by whom? Boron. So that means the shape of that molecule is closure. Okay. Next one, let's see the Nido. Next, let's do the Nido. Okay. Okay, Nido. So what is SEP? SEP is equal to, so number of borons. How many borons do we have from this formula? 5, and each boron contribute how many valence electrons? 3. Then plus how many hydrogens do we have? 9. 9 into 1. 9 into 1. So now this time we don't have any charge. So that that whole thing should be subtracted. Whole thing should be subtracted minus 2 into how many BH bonds we can expect? So obviously 5. How many? 5. Sorry. 5 divided by 2. 5 divided by 2. So that will give the formula of SEP. And so now SEP is equal to, so how much? 5 3 is 15. 15 plus 9 how much? 15 plus 9 24. 24 minus 10 that is 14, 14 by 7 again, 2 again 7. Now this 7 further equals to n plus 1. So n plus 1. So but where number of vertices are number of boron atoms is equal to n minus 1 equals to n minus 1. So now how many boron atoms we can expect? How many boron atoms do we can expect? So according to this formula, n is equal to how much? N could be how much? Further n is equal to how much? Yes. Further n is equal to how much? 6. Okay. So n minus 1 means 6 minus 1. 6 minus 1 is equal to how much? 5. Is equal to 5. So that 5 is what? Number of boron atoms. So as per our formula, how many boron atoms do we have? 5. So that means what is the shape of that compound? That is needle. So with the help of this, we can, by Wade formula, we can calculate the n value. With the help of n value, we can calculate number of boron atoms. This based on this SEP n plus n value and this vertices occupied by boron atoms that can be obtained from are obtained by n or n minus 1 or n minus 2. So on the basis of that, we can categorize the shape. We can categorize the borons into arachno, closo, and nido. If n is equals to number of boron atoms, then the shape will be closo. If n minus 1 equals to the number of boron atoms, then that shape is this one, second nido. And if see here all the how many vertices do we have? Okay, I will show you with a pointer. Okay, I will show you with a pointer. Okay, see how many vertices? 1, 2, 3, 4, 5, 6. All these vertices are these vertices equals to n. So if all these vertices are occupied the boron atoms, so then the vertices equals to the number of boron atoms, then the shape of that compound or boron is closer. So here see in this case all these are see polyhedron or you can say octahedron. So here see out of 6 vertices only how many boron atoms are occupied? 5. Just now we have seen last example. In that last example, n is equal to 6. So n is equal number of vertices, and but how many boron atoms do we have? 5. That means n minus 1. So that equals to 5. So at that time the structure of that boron is nil. Next another one is again we have how many vertices? 6 vertices, but how number of boron atoms equals to n minus 2. So that's why here see 4. So these two are vacant, or these two apexes are missing. So that statement we quoted in that slide. So by this manner we can identify the structure of what? The structure of borons. Okay, so this is continuation to this. If carborans is a nothing but a cluster compounds of carbon and borons. Uh, in short, we can say carborans. Now, okay, borans and carborans. Carborans are nothing but cluster compounds of boron, carbon, and hydrogen. So just now, before this, we have studied about borans. In that borans, we have two constituent elements. One is boron, and the second one is hydrogen. But in carborans, we have three constituents. One is carbon, second one is hydrogen, third one is boron. Okay, so again see now this the atoms likely may have related to boron lekane untai, and these clusters are polyhedron and are similar, classified as closonido and arachno and hypo etc. based on whether they present a complex complete closo polyhedron or polyhedron that is missing one. Same, missing one means the one vertex or apex is not occupied by our uh, either carbon or boron. So if two are missing, then that is Archer. If more than that, then that shape may be this one, hypo. Okay. And icosahedral closoboranes are partially stable, and these boron-rich cluster exhibit unique organomimetic properties. Organomimetic means similar properties. That means these carboranes exhibit similar properties to that of organic compounds. Okay, and like chemical reactivity and classical origin molecule at structurally similar to the metal based inorganic compound, okay, organometallic compounds. A prominent example is in the charge neutron. So this is C2H10B10 12, or we can say orthoborans, which is the prefix O derived from ortho. Okay, and this derivative has been considered for a wide range of application for heat resistant polymer to medical applications, particularly in medical or in the medical field. We use this one. The electronic structure of these cluster compounds has been described with the Wade and Mingus rules. Okay. So this is about carborans are closely related to borans. The stoichiometric and structural similarities and differences arises from the fact that, yes, why these are a bit similar, dissimilar or different from the borans? Why? Because here we have what carbon atoms, and the valency of that carbon atom is 4, more than one valency of boron atom. Consequently, whereas the boron hydride, that is B5H9, has a nido structure, just now we have studied nido structure, the corresponding carborans of 1,5, this one, see here, see B5H9. So how many how much we can expect the SEP7, and here in C2B3H5 also a close. Oh, why? Because so here 4 plus 9 plus 5, 4 plus 9 plus 5, how much? 9 and 18, and here okay, structure. So 1 5. So that means these carbon atoms are present at first and fifth position, and in between we have borons. Okay. So similarly, the carborans closo 116 C 16 means at first and sixth position we have what carbons. In between we have what borons. Is a isoelectronic and isostructural with the closoboran anion. So B6H6 hexahydro hexaborate. So whose core is regular octahedron? Yes, it is octahedron. Why? Because it has 6 vertices, and 6 vertices are occupied by 6 boron atoms. So similarly, this also may have 6 vertices, and all these 6 vertices are occupied by 4 boron atoms and 2 carbon atoms. Okay, so and this is example, you work at it. Okay, so I hope you have understood this. Thank you very much.